All right. How you guys doing? Better or worse today? I don't know. Um, I'm doing a little better than Tuesday. That's for sure. Wasn't able to be here, as you know, um, but still not great. I've got some hand sanitizer up here, so I'm going to be dousing myself with that for your sake before I hand these back. I'm going to hand out the exams, and then if you just don't want to be anywhere near me because I'm sick, just shoot me away. That's fine. Come get it later. And good news is most germs tend to die when they dry out, so if they're sitting on the exam and we wait a week, probably a little safer. But I probably got it from you guys anyway. So, um, got a question? Yeah.
Did you happen to drink some of the Milwaukee treated water?
Nope, I do not have cryptosporidium. That's going to view online. It'll take a few minutes, and I'll be back. All right, and I apologize if I get names wrong or poorly done. I'll do my best. There were a few people that had to take a separate exam. I guess I'll make a couple comments here. You'll see that I added points to most of your exams. I decided that I really didn't like how much of an impact the multiple choice was having. Probably weighted too heavily. So what I did was I took on, for most of you, the first page, whatever points I took off there, I returned basically half, rounded down, but half of those points back. So it kind of effectively made a curve for you. If you were missing a lot of those problems, I didn't feel like it was a great gauge of your knowledge compared to the rest of the exam. And if you had to take the makeup a different exam, took the second page and did the same thing to kind of make that even. So you'll see that the plus number, that has to do with that. If you aced the first page, great, you got more points than anybody else did on that page, so that's just that. There were a few, as you can see, a few A pluses, even one. Remington Guillory? Long Tran? Jack Goosey? Andrew Arlogaga? Tommy Michael? Grant Luke? Paul Manasco? Dylan Cook? John Taylor? Connor McCrossy? Garrett Kramer? Andrew Jewell? Camille Sewell? Jacob Reinhardt? Layla Hansen? Bryson Williams? Jose Avalos? Jacob Lee? Guy Sam? Annie Henderson? Catherine Mole. Hayden Walls. Brooke DiMaggio. Tyler Nemitz. Beverly Smith. Trent McKinney. Blake Ridavu. Ashlyn Williams. Julian Oak. Andrew Dietz. Ricardo Silva. Emily Newell. Devin Stahl. Taylor Miller. Christian Nelson. Gabriella Houston. Colby Rapp. Aubrey Odell. Luke Aguilar. Sam Haskell. Leslie Castaneda. London Levy. Jacob Skifelsky. Diana Abbey. Barrett Carraro. Max Torabal. Israel Manzano. Madeline Luther. Kaylee Fasten. Matthew Ryrick. Tim Hewin Truitt. Gracie Fournier. William Shiel. Dakaria Smith. Jonathan Harkey. Zach Brookstein. Do you know formula? Grace Cage? Emma Connor? Lily Crocker? Cameron Hill? Luke, Fitton? Ethan McDevitt? Mason Rawl? Ethan West? Macy Tumble? Alexis Kira? Anthony Glenn? Natalie Johnson? Jeffrey Dakota? Ethan Nook? Haley Pittenger? Connor Ortega? Ben Vanderbrook?
2 zeros.
Oh my gosh.
Xander Hughes? Come forward for me real quick. Today?
My first name's spelled kind of weird.
Is what?
I said my first name's spelled kind of weird. It's Cal.
Actually, what I'm going to do, since you're all, with everybody, I'll just read them out again. I read it wrong. I read it fast. Kaylee?
The Cal. Yeah.
Sorry.
Thank you.
I'm going to just try to read through this. Andrew,
Yeah, do you know if this will obviously be
I just had you. You really stopped my mind. Yes. Sorry, I was like, telling you something that also like.
Oh, you're supposed to.
All right. So let's take a quick look at it. So the first page, I'll go quite quickly through the first four here. First one was talking about primary or secondary standards, kind of what's enforceable, what's not enforceable. This is just kind of the big picture about drinking water in general. And basically anything that could be hazardous to human health is primary standards. So stuff that's not related to primary standards would be hardness. So the fact that hardness does not impact human health is the reason that one's not included in the primary standards. Number two, which is the most difficult to remove by sedimentation. Really what we're looking for here is the size of the particles. And we took a look at that graph, talked about it, tried to get an impression for what size things these are. And I also tried to give you, well, actually, no, this one I didn't. You could kind of see that just thinking about it, hopefully you knew or remembered that viruses would be the smallest one. So those are never going to be removed by sedimentation alone. Next up, we had a true or false batch reactor containing some substance. And the statement is that it can reach steady state with respect to that concentration with exactly one reaction occurring that affects C. So if we talk about our mass balance, we're always talking about V dc dt, so the accumulation within our volume. And in a batch system, we have nothing going in and nothing going out. So it's like Q goes to 0. So the in minus the out both go to 0. And then we have a reaction term. And if we have exactly one reaction term, it doesn't matter if it's plus or minus. We only have one of them. And therefore, this part can never be 0. If we have exactly one reaction, this cannot equal 0. Because 0 cannot equal to something. Cannot be equal to something. Because it does contain some C. So even if this depends on C, there's some C in there. It can't go to 0. So that should be false. Next up, this is probably one of the trickier ones because I never talked exactly about the Dead Sea, so you might not have known that. But I did try to help you a little bit, making it increasingly salty as we go up. And hopefully you remembered that salt, or ionic strength more accurately, is the more of it you have, the more likely to destabilize particles it was. So it was kind of testing that knowledge. And so even if you didn't know how salty the Dead Sea was, you would be able to say, well, distilled water should not have much at all. And rainwater probably doesn't have a lot. Mississippi River water has some. We did talk about Lake Pontchartrain being kind of salty. So hopefully you kind of got that idea. And so the closer you were to the top here, the more accurate you were. The Dead Sea, by the way, is much saltier than ocean water because it's essentially a lake that has an input but no outputs. So in terms of a mass balance, the only place the water can go is to evaporate, and the salt doesn't evaporate with it. So it's just accumulating salt. It's actually very close to this VDC dt, right? It's just slowly accumulating salt as water brings salt in and evaporates and leaves it there. So that's why you can float on the Dead Sea, because it's so salty, so dense. So anyway, like I said earlier, I didn't feel like this was the perfect gauge of your knowledge. So if you're feeling salty about getting the salt wrong, just look at the extra points you got back and be a little less salty, I guess. Okay, speaking of salt, next problem we have essentially a challenge to calculate salt concentration given some example aquarium. So in a 150-liter saltwater aquarium, I'm going to use this table, certain amount of sodium chloride and calcium magnesium carbonate added. I give you the amount of each and the ions that will be present from that. And I ask you what is the resulting, first of all, what is the resulting concentration of calcium? So we're looking for Ca2+, and I want that in moles per liter because you're going to have to calculate for the ionic strength, which requires that. Anyway, I even put a gram per liter value here, but that's the wrong answer. So even if you solve for grams per liter, you still need to convert it back to the correct answer was D. And just a quick explanation here for you. We've added 75 grams and 150 liters. So that's going to give us our gram per liter concentration. And we're first going to look at this guy, right? So that's 75 grams of calcium magnesium carbonate. And the reason that this is equal to half a gram per liter, but the reason that's a wrong answer is because a lot of that half a gram is magnesium, and a lot of it's carbonate. So it cannot be half a gram per liter of calcium directly. It would be less than that if we were calculating on a mass basis. So we have to take that, and then we need to get the molecular weight of this calcium magnesium carbonate. Turns out, do that math, it is 184.39 grams per mole. And so we can take that, the half a gram per liter that we calculated, and essentially divide it by that 184. So we'll have 1 mole per 184 grams of this. And when we do that, we should get a value here that's equal to 0.00271 moles per liter of this calcium magnesium carbonate. Now, every 1 mole of CaMgCO3 will give us 1 mole of Ca2+ and 1 mole of the magnesium, and so on. So it's a 1-to-1 ratio, so that becomes our answer. Because we could write this as moles per liter of the calcium magnesium carbonate and multiply it by 1 mole of calcium per 1 mole calcium magnesium carbonate. Okay, so to be thorough, that's the way you do it. Does that make sense? All right, I tried very hard to make some tricky alternate answers that were wrong. So I guess some of them were selected. But I think on that problem, and I know on this next problem, I actually didn't take as much off in the first place because the way I was scoring these was the first 4 were 5 points each, and then this one that was calculated would have been worth 10 points, and then this one would have been worth 10 points. So if I saw some effort, I think I went ahead before I even decided to do the plus points for you. I decided for this one to not go so hard on it because a lot of people were missing it. So if you didn't show me any work and you got the wrong answer, I probably took off more like full credit. If you showed me some work that was in the right direction, I went ahead and started my partial credit type of approach at least a little bit. So what I really wanted to see, well, first of all, the right answer was C. What I wanted to see was you taking a look at this equation and putting it in properly. So the ionic strength would be calcium concentration times its charge squared plus the magnesium concentration, which turns out will be the same, plus its charge squared. And then we also need chloride times its charge squared, which is just -1 squared. I'll just continue here. And carbonate times its charge squared. And we need sodium too, times 1 squared. Okay, I wanted to see that, which means you needed to calculate the sodium concentration, basically each one of these concentrations. We already calculated 2 of them because the calcium will be equal to the magnesium. Another reason I didn't really care to take off quite as many points here, if you got 5 wrong, then you were going to get this one wrong, very likely, unless you had a good guess. So I didn't love that setup. So this one should equal Cl minus, and when we do that, it's the same process as before. We're just calculating the 75 grams that were added, 1,200 grams that were added, and with a molecular weight of sodium chloride. This turns out to be 0.137 moles per liter. So that's there. And the chloride, the carbonate is just going to be 2 times the calcium. It comes out to be 5.42 times 10 to the minus 3. So with all that, you put in the stuff, and you get the ionic strength of 0.159. Any questions, issues? All right, so next up we had a kind of a mass balance problem. It's touching on some wastewater topics, but I did write here, you don't need to know anything about this BOD stuff. Turns out it's kind of just a generic way to describe microbe food. It's just a waste stuff. So this is really just a mass balance problem to test you on what you've learned about mass balances. And so here we have this conventional wastewater plant treating some flow. We have a hydraulic residence time. It's going to be a CSTR removing, and we're given a rate constant here. And what you'll notice, what I hoped you noticed, was the units here are not first order. These are 0 order units, so we have a 0 order rate constant to deal with. That's going to affect our mass balance. So it says answer the following questions about the system. It operates at a steady state, and don't worry too much about BOD, it's just something we're removing. So we're just going to say the concentration of BOD, we'll just call it C. Sure. So what is the effective volume of the primary treatment? Well, we need to know, essentially, we need to use our hydraulic retention time to find that. Because we don't have volume, but we have a flow rate, and we have a hydraulic retention time. Q is given 0.44 cubic meters per second. And theta was 15 minutes. That would be 900 seconds. If we convert that, so that would give us a volume of 396 cubic meters. Part B, we have, so if we have some influent concentration of 450 milligrams per liter of BOD, what will the BOD and the effluent be? So given these parameters. So we're looking for C, right? C and the effluent. As always, it probably helps to draw the system. So we could have some flow going in, C not going in, C going out. C is the same thing in here. We have some volume there. And then we have this reaction with that rate constant, 0.05 milligrams per liter per second. So we need to set up a mass balance. We were told it's at steady state, so we'll go ahead and start with 0. No net accumulation in the system. It's going to be equal to QC coming in minus QC going out. That's all normal. And then we have our reaction term. It's a plus, but it's a decay, so we're going to say it's negative V. And here's where we put in our reaction term. So here's where it's important that this is a 0 order, not a first order, because here we would say V times K times C to the 0 power, or just get rid of it altogether, because it's going to go to 1. And that's where many of you would have made a mistake if you messed this problem up. And if you did, I could see your answer was something like 9.3 or something like that, or maybe that was the percentage at the end. There was some typical value you'd get if you did everything right except put it in first order. So I didn't count off too much, but that was wrong. So if we derive from here, trying to solve for C, add QC to both sides, or let's divide everything by Q first, actually. So C0 equals C naught minus C minus theta K. Add C to both sides, we get C equals C naught minus theta K. Turns into a pretty simple problem. The type of problem you could do without any calculus or mass balance kind of stuff. So when you put that in, C should be 405 milligrams BOD per liter. Okay, make sense? All right, so not a big change, right? We started with 450, we ended with 405. So to answer part C, we might know that we didn't even remove half of it, so not a lot. If you had a first order system, I think you're removing something closer to 90 or 95%. But essentially what we're looking at is the efficiency is going to be what we started with minus what we've removed, divided by what we started with, multiply that by 100%. Just a pretty standard way to calculate it, and that would be essentially 10% efficient. So we start with 450, we end with 405, we're removing 45 milligrams per liter, we're removing 10% of the stuff. Does it make sense? All right. Number 8, we're treating Lake Pontchartrain as a large basin, kind of seeing what it would be like if we tried to use it as a big sedimentation chamber. So we give it some dimensions. We talk and we say, okay, if the Bonnie Carr spillway is going to discharge from the Mississippi, we're going to bring in these certain particles. What's going to happen to them? How fast are they settling? And what is this large sedimentation basin kind of acting like? So part A says calculate the critical settling velocity, or rather the design velocity, either one you want to call it, of the basin under these conditions. Now, a lot of you were thinking backwards here. Bless you. And most of you corrected that eventually, but you ought to recognize if you did this backwards, if you flipped A and B, recognize that you were not properly interpreting what the question was asking for. You were a little ahead of yourself. You're like, oh, I've got particles, I can calculate a velocity. Maybe that was you, maybe it's the stress of the exam. But I was asking for the critical settling velocity, which is actually a simpler question. That's a V naught, right? So I wanted, first, for this basin, what is that? And we were given the flow rate, and we can calculate the area. And by the way, the numbers here I kind of estimated from Wikipedia. So these are quasi-realistic in the sense of the scope, not so realistic in the sense of the actuality. There's going to be a lot of mixing and turbulence from wind, if not anything else. So don't take this as like the real deal, but scope-wise, it's pretty similar. Okay, so if it was perfectly still and laminar and all that, then this would make sense. And we could calculate our Q was actually given as 7,700 cubic meters per second. That kind of incorporates what at least Wiki had to say about is it Bonnie Carr or is it Bonnie Carr? Bonnie Carey, that's the one. Okay, yeah, not a local, can you tell? Okay, Bonnie Carey. I think it can't quite discharge this amount, but there's some of the rivers that flow into it adding some flow as well. So this, like, those two combined is kind of like the max we might expect. Anyway, the area was 1,600 square kilometers. We can convert this into meters, would be very convenient. So this is one potential area. You had to make sure you get this right. You're going to have 1,000 meters per every 1 kilometer, but we need to convert the squares, so we have to square the whole thing, right? Or you could look at it as you're going to square the top and the bottom. 1 squared is still 1. And so this conversion here makes quite a difference. So we end up with the area of the basin at 1.6 times 10 to the 9th meters squared. Given that, we can calculate our V naught at 4.81 times 10 to the minus 6 meters per second. Okay, so pretty slow, but these are small particles. I mean, actually, that's the design velocity, right? So it can remove some pretty slow particles, basically. Okay, and again, not super realistic, but would certainly have a lot of sedimentation if it was, if it was still and not windy. So B, calculate the settling velocity of the particles described. Here's where a lot of you realize, oh, yeah, I did that backwards. That's fine. As long as you showed me that you knew which one was which, I was fine. So here's our equation where we need the gravity, the buoyancy of the particle minus buoyancy of the water times diameter particle squared divided by 18 times the viscosity. Okay, with that, just real quick, the particle here, the correct density was 1,100 kilograms per cubic meter. Density of the water at the conditions given here was 997. Diameter of the particle was given at 10 micrometers. You could say that's 1 times 10 to the minus 5th meters, however you want to express it. And mu was 8.9 times 10 to the minus 4th kilograms meters per second. Per meter second. Okay, this all came out when you put it in. The Vs should be 6.31 times 10 to the minus 6 meters per second. So when we compare those two, this one is faster, so technically they're all going to settle. So Vs is greater than V naught. So without any math, we could say 100% removal, or you could do the math and get some number there. If you gave me a number above 100%, I might have docked you a point for being silly. I don't remember exactly, but it's not possible to remove more than 100% of the particles. So that was a wrong answer. In part D, we change the temperature. It's winter time, the water gets cooler. We're at 10 Celsius. So essentially, we just need to calculate a new Vs at 10 degrees Celsius. Now our density of the water is going to be slightly more dense, 999.7. And our dynamic viscosity gets a little more viscous. So it's 1.307 times 10 to the minus 3rd. Okay, we get a new settling velocity at 4.182 times 10 to the minus 6 meters per second. And what percentage of them will be removed? Well, it's not going to be 100% because if we go back, 4.1 is lower than 4.8. I did not mean to make them both 8.1 and 1.8, so that didn't mean to make that slightly tricky there. But Vs over V naught comes out to be, if we take that and multiply it by 100%, comes out to be 86.9. Okay. Any questions or issues? All right. So last problem, we had jar tests. It's a common way to kind of check how effective a coagulant is. And so in a jar, it's 10 times bigger than this guy, so 10-liter jar. It's what we're going to use to measure coagulation. We're going to put a stirrer in there to keep it moving. It's 20 Celsius. We have some number of initial particles in the jar. And they have there are 40 micrometers in size. So part A says if the stir is powered by a motor, we've got 7 milliwatt motor. What is the mixing intensity of the jar? So here we just need the power divided by the viscosity times the volume. So here we need to know that we need power in watts and we need volume in meters. So 10 liters is going to be 0.01 cubic meter because there are 1,000 of these guys in a cubic meter. So you do that conversion, we'll get that. And the power is going to be, so that would be our volume. Power is going to be 7 milliwatts, which is 0.007 watts. Put in those numbers, you should get a G of 26.43. The units here are per second. So keep in mind, it'd be very good to know and track your units. Some of you were neglecting units. Again, it would be quite helpful for you to prove to yourself that things are going correctly with that. Okay, so part B says assuming the coagulant caused complete destabilization of the particles, what that means is our alpha is equal to 1. What is the average number of single particles in an aggregate after 30 minutes? Now here's why we talked about this a lot, and I told you repeatedly that I wanted you to know what this type of phrase meant. Wanted you to recognize that you can get the number of single particles in one of the original aggregates with this equation, right? With this expression. So n naught being the initial particles per volume, and n being the number of aggregates per volume, that ratio gives us exactly the number of single particles in an aggregate after some time. Okay? So if you weren't trying to find that, you were definitely doing something wrong. And you would have been a bit lost. Okay, the other tricky part here, we just looked at the volume, and I was hoping that that would connect with you, but I didn't actually give you an n. So here, many of you thought that that was n, but that's not true. Or excuse me, n naught. And the reason that's not true is that's some raw number of particles in 10 liters. So you need to convert that into per cubic meter to do our future calculations. So n naught is going to be equal to 2.5 times 10 to the 7th particles per 10 liters. And then we can multiply that by essentially 1,000 liters per cubic meter. We can just do it that way, 1,000 liters per 1 cubic meter. So we need to account for the 10 there and that conversion. So some of you got part of it, some of you probably didn't get either. I don't know. So do I have this number? Should be 2.5 times 10 to the 9th particles per liter or cubic meter. So that's the n naught that you needed, and you needed that in order to find omega so that you could find k. So ultimately, we need the k because we're going to do this as a first order reaction in a batch. So essentially, as you will remember, we could take ln of n over n naught is equal to negative kt and take e to the power of both sides to get n over n naught equal to e to the minus kt, and ultimately get n naught over n is equal to 1 over e to the minus kt. Right, so that's where we're going with this. That's the expression we need. So we need k. We're given t, that's 30 minutes. We have to put that in seconds. But once we do that and we get a k in per seconds, which is what we're after, then we'll be good. So we need the omega, and to get there, we need the proper n naught, and we need all these pieces. So we need alpha times 4 times, oh, excuse me, ahead of myself. K is alpha times 4 times omega times G over pi. The omega then is the flock volume. This is pi times dp cubed over 6. That's the volume of one particle times the initial number of particles per volume. If we put all those volumes into cubic meters, then it's going to be a volume per volume. And remember that as a way to check yourself, the flock volume can never be above 1. That would mean in some volume, more than 100% of the volume is particle. That's not possible. So flock volume on a volume per volume basis cannot be above 1. It's got to be some fraction. Okay, anyway, so this turns out to be, where did I write it? When you solve it, you get 8.38 times 10 to the minus fifth for that, and K would come out to be 2.82 times 10 to the minus 3. Per second. That gives us an n over n naught at the end of the day, excuse me, n naught over n of 159.9, or basically 160. I'm just going to leave it at 160. Of course, we had to put K into seconds. Should be 4,600, 4,800? No, 1,800, sorry. Handwriting. Okay, does that make sense? I know a lot of you struggled on this one. Fortunately for you, for this particular part of the problem, I was only counting a total of 6 points, so shouldn't have counted off too badly if you completely botched it. All right. Last, we have what happens essentially if we change the situation and the coagulant's not as effective. We're only getting a 40% particle destabilization. Essentially, the only change here is now our collision efficiency is 40%, or 0.4. And then we get a new K, which is 0.4 times the old K. Or you could simply say, or put that becomes 1.13 times 10 to the minus third per second. So K nu, easy way to do that is just to say K nu is equal to K times 0.4. Okay, then you put in the equation again. 1 over e to the minus kt with a new K, same time, and we should get 7.61, and maybe round that to 8, because I kind of asked the average number of single particles, right? So I was going to accept either one on that. I would not accept it on a how many filters type of question, because that's a little more practical and you have to round up no matter what. So for granular filtration, I would not accept this, but for this one, that's fine. All right. Any questions? So if you did have the makeup exam, I know things were different. I think the problems are pretty similar. So feel free to talk to me if you wanted to catch up on that. All right. Be done with that. We'll go on to some membrane filtration. We've got about 20 minutes, and since I had to cancel class, I'm going to try to give you the big picture overview here before we let out, assuming my voice can hold. All right. So last time we were talking about filtration, we were talking about granular filtration. We talked about the different mechanisms and kind of the reason it works, kind of the setup, how to calculate some math with them. Today I want to talk about membrane filtration. We did look at this slide already. Essentially, we are normally considering physical size exclusion, where some particle will get stuck and be prevented from passing through a membrane. Now, a membrane is a fancy word for there's a few definitions of it. A thin, pliable material that some things can pass through would count as a membrane. So you could see some things could pass through it. If you look at the proper angle, if I had a light behind this, if I just use my phone, this will be a better demonstration. Some light is not passing through, obviously, or making a shadow, but you could also see that some light is passing through, right? So you could see, okay, in that sense, it's kind of a membrane. Some stuff's going through, some stuff's not. If I were to hold it still and pour my water bottle through it, chances are good some of that water would make it through. Okay, it's a porous material, it's a membrane, counts. Now, if we get really, really small with the pore size, some other stuff starts happening and it's not precisely size exclusion, so the reverse osmosis stuff, don't worry too much about that, but it does get the physics get a little funny when we get really small. But in general, membranes will be a size exclusion type of thing. So the definitions here, or rather what we use them for, would typically be particle removal. We can use it for virus removal. We just have to have a pretty small filter. So if we're just doing particles, essentially the same function as a granular membrane, a granular filter, we might say this is kind of on the order of microfiltration. You could pass water through a microfilter and visibly clean it up, but anything small enough that you can't settle it is probably still coming through. So very fine clay particles might be making it through, maybe not, but some of them might. And viruses and bacteria would probably be mostly making it through, depending on the size exactly. But then if you want to get smaller, you go to ultrafiltration. I would say the small end, and we'll see a graph of this, the small end of microfiltration is kind of on the micrometer scale, is getting you some bacteria, or maybe all. When we start going to what we call ultrafiltration, this is kind of between the micrometer and the nanometer scale. This is starting to remove viruses, definitely getting our bacteria out of the way, and any other colloidal materials. So if you made some coffee and sent it through a microfilter, you'd get all the remaining coffee grinds out, but it'd still probably be kind of a brownish color. If you then pass it through a ultrafilter, a lot of that color that you have is probably coming from small particles. So a lot of that color would be removed. It might still be stained a little bit. If you think of tea is mostly molecules that are coming out. If you kept all the tea leaves in place, it's mostly because you can see through it, right? It's clear even though it's brown or green or whatever kind of tea you have. So if you are getting these, the molecules are still there, they could pass through a nanofilter, an ultrafilter, and eventually, if we go small enough, we can start collecting those. But the tea for the would probably remain colored after passing through an ultrafilter. Okay, if we want to get rid of all the colored molecules, any molecules that are bigger than a water molecule, that's when we're getting to reverse osmosis, and kind of nanofiltration is kind of on the end there. So you can kind of think of these on the micrometer pore size, and the ultrafiltration is kind of between micrometer and nanometer. Nanofiltration, of course, is that nanometer scale. And reverse osmosis is kind of, when we're getting that small, things get a little funny, but it's kind of like saying less than nanometer-ish. Okay, already covered the definition, a thin pliable sheet or layer, especially of an animal or plant origin. So you might think of like a cell membrane. We use that term a lot. Or the membrane, you might say, bless you, the tree bark is in a way a membrane. Probably gases and things can pass through it, but it's protecting it. Or there might be some like cellular material underneath the tree bark that's a membrane. Might be a better concept. So that you can think of different things. If you've ever dissected an animal or maybe filleted a fish or something, you'll know there's some membranes you might have to cut through, or you might encounter thin pieces. That's kind of the animal or biological origin. Could also be a piece or parchment forming a part of a roll. And we'll see some examples of how we set up membranes for filtration in a rolled type manner. So membranes are kind of one of the new-ish water treatment technologies. They've only began to be used for water treatment something like 60 years ago. More and more common about 30 years ago. So it's kind of new, but pretty well studied by now. The pore size is inversely proportional to the pressure required to push water through. This is going to be very obvious when you stop and think about it. If you've ever done any filtration in a lab, like a little syringe, or worked with anything that clogged up and it's harder to push water through it, or if you've taken a hose and you made the pore of the hose smaller with a nozzle or with your thumb or something, you'll know, it's harder to push water through it now when we have a smaller pore, right? That's just kind of the way things go. So the pore size, smaller the pore size, the more pressure required, but that means we can use small pores if we need to. All right, the typical terminology we're going to talk about the process of membranes in a few ways. One is we're going to have a permeate. That's a fancy term for the stuff that went through the membrane. Permeate, it permeated the membrane. It passed through. So if we had some membrane, just doing a flat sheet, water's passing through. What goes to the other side has permeated it, so that's the permeate. We'll have a feed. So what are we giving to the membrane? What are we treating? We are feeding water to the membrane to create some permeate. And then another thing that we can set up these systems where we actually have two outlets. We could have water crossing and then water being retained, and this would be a concentrate. We could also operate in a way where we're not retaining a flow, but we're just retaining some of the water. You can imagine if I poured this into a little filter and I let it filter halfway through, whatever's remaining in here is now more concentrated, because whatever was rejected, let's say I had some M&Ms and I poured this into a coffee filter. I started with 10 M&Ms per liter. I poured out half a liter to the coffee filter. Now I have 10 M&Ms per half a liter. So I've doubled my concentration. Okay? So when we talk about membranes, we have to consider the mass balance, but it's pretty simple. The only issue is, what is our separation doing and how are we accounting for that? And maybe we'll solve some problems as well in terms of how much pressure and therefore power, things like that, do we need in order to treat what we want to treat. So big picture here is we need to keep in mind the three possibilities of where the mass can go. Right? From the beginning of this class and onward, we're just concerning ourselves with where is the stuff going, how much separation are we getting, how are we tracking that mathematically. So knowing the feed, the concentrate, and the permeate, and the similar terms for these are going to be important. So a feed or an influent maybe, the permeate here, let's see, I guess maybe in some cases we might call that an effluent. If it's like in the context of wastewater, occasionally we use membranes. That would be a membrane bioreactor effluent, could be a thing. The concentrate, sometimes we might call it a retentate. You'll see that it's kind of intuitive, kind of obvious, but it could also easily confuse you if you're in the middle of an exam or something, right? Okay. And so this is another way to describe the concentrate or the retentate is this is the stuff that was rejected. The membrane rejected everything in the water that's there. So if we're rejecting those M&Ms with the coffee filter, they are in that portion of the water. Okay, there's a couple ways we can set up a membrane. This might make it a little more obvious as to why we would have some concentrated flow. If we set up a membrane so that here is our membrane, we can see there's some pores for water to go through. We are feeding this whole system, and what this would really kind of look like in practice would be we would have some container, right? We have some container that pressurizes the water so that it's encouraging some of it to go through. So over here, we probably have some constriction or other way to apply pressure to the entire system. Letting water come out, but providing some kind of pressurization. So we'll have this whole system pressurized. We would usually apply a pressure from the feed. Sometimes we would simply apply a vacuum on the permeate. So that's an option. We could use gravity to be forcing water down. So there's a lot of options we could use. Just to clarify, it's not always a vacuum. At any rate, we'll have some water flowing across our separation layer, our membrane. Therefore, we will have cleaner water coming out the permeate, and we'll have dirtier water than we started with coming out the retentate. So pretty obvious, pretty straightforward. I do want to call your attention to when we do it this way, this is called cross-flow filtration. We have water, it's flowing across the membrane, and some of the water is going through the membrane, but the fact that we are flowing water across it and taking out the concentration of contaminants with this wasted retentate water, it's actually not necessarily waste. If you've ever had, who's had orange juice from concentrate? Anybody? Or any kind of juice? Well, from concentrate. What does that mean? They've passed their orange juice through a filter to make it weigh less by getting rid of some of the clean water. They take all of the stuff they concentrated, that's all that tasty stuff, and collected it in a jar, shipped it somewhere, then added water, or maybe you added water, and now you have orange juice from concentrate. You just didn't have to ship all that water. That's the deal. So that's why you do it, and that's why you've seen that in the stores. So essentially, all this stuff over here, maybe you're collecting it. Usually in water treatment, we're not collecting it, but who knows? Maybe you're selling orange juice and you want that pulp. Okay, and all the other flavor molecules. So that's the example here. And one thing that's really nice about doing cross-flow is if you're doing a continuous system, you don't want all these particles sitting here clogging up the membrane. They will accumulate and accumulate and accumulate if you're not letting them go anywhere. So doing cross-flow helps take all these guys and send them away. Otherwise, if they had nowhere to go, if it was just one flow in and one flow out, you just build up a layer. And that would be called dead-end filtration. So I think I've got another, yeah, we'll talk more about that in a second. So when we draw a schematic for a filter, this will be a common way to do it, to have some feed coming in. And then we're just going to draw some sort of diagonal inside a box. It could be this way, it could be this way. Doesn't really matter too much. What you need to pay attention to is there's water being rejected and there's water permeating. So you see I have four little arrows here. One going in has to be the feed. 3 going out. One of them is going to be redundant no matter which way we draw it. So I just want you to recognize whether or not the flow has to cross that barrier is what matters. So in this drawing, here, the one that does not cross it would be the retentate. And these two are the same. That'd be the permeate. You don't have to draw 2, but as long as you're labeling everything correctly and understanding what's going on, doesn't really matter. Even in this diagram, right on the left, we could count that as like a bunch of different flows that are making their way through the membrane, but they're going to be collected into one spot. There'll be one permeate. Okay? Yeah. That's just convention. So it's convention just to put a line like that. What it does is it kind of distinguishes whatever's on the right side of this is the permeate. Whatever's on the left side of this is the retentate. So it doesn't really matter too much. You could draw it this way and then flip what I just wrote, but I'll leave it this way. If you drew it vertically, it would not make much sense because you don't have a way to separate them so well, right? You'd have to say, oh, I'm going to draw one out here, and that's my retentate, and then over here. I mean, I guess you could, but we're just going to go with convention. Draw a nice little horizontal or a diagonal. Now, if we have the dead end filtration, so that's all cross flow, the dead end system, we would draw a little just horizontal type of thing. I've got more slides on that, so we'll come back to dead end. So we've got these two versions. We just talked about the cross flow. Again, doesn't really matter too much. Once you draw it, you could get rid of the redundant one here. That would be fine. Or just plan to draw it with 3 in the first place. The dead end, the deal is, as you see in the little picture here, a lot of times we'll have some filter. Maybe it's a little disc filter or something. We'll apply our water. And actually, what I'm going to do, I'm going to draw this a little different. We're just going to draw the filter kind of at the end here. So that's the filter. Draw it better. There's our membrane. And then we might have some amount of volume here. While we're pushing on it, while we're operating it, we will have a feed and a permeate. But maybe we stop at some point and say, okay, we filtered enough and we're not going to push the rest through. That's also possible. So we could then have some water remaining that maybe we want to collect. Say we're making some orange juice concentrate in a little syringe, right? We would push 80% of the water through. We've concentrated the remainder, and we have a concentrated volume remaining. So the only difference is we could operate this with a volume instead of a flow type of basis. So if we're doing dead end, this is more like a batch process. We're doing a certain amount of it, and that's that. If you've ever been in a lab doing some sort of sampling, you may recognize if you've got some sample you're trying to clean or whatever, it doesn't take long before one of these fills up with gunk and you have to get a new filter. And you're literally sitting there pressing with your thumbs with all your might until you blow up the filter. No, that's never happened. What are you talking about? Yeah, that happens, so you got to be careful. So often we will take these on volume basis. I'm just going to say often. Whereas these guys, since they're continuous, this will be a flow rate type of operation. You could operate a dead end with a flow rate until the filter clogs. So I'm not saying you can't do that. Just typically, I think we'll have a practice problem next time. We'll do a syringe type of thing, and we're going to take a look. Okay, we did this much mass with this much amount of volume. So it'll be a little more dealing with concentrations and things like that. Okay, another example here of a dead end filter. If you've worked in a lab, you may have seen something like this before, where you have, you might fill it up with some water. You apply a vacuum, and you have your membrane. You place your membrane right here. So in this case, essentially you're pulling water through. This would be your feed. And again, you can kind of see, you would just pour some water in that, and it'll be a batch process. And then you'll have the liquid should pass and drop through here, and that'll be your permeate. Again, just kind of a dead end mode here. So just another example of a typical one. Now, one thing you might notice in this particular setup is you're actually limited to the amount of pressure that's in the atmosphere. Even if you draw a perfect vacuum, the pressure pushing water through is only the amount of pressure that's in our atmosphere. So these types of filters would work a lot better on the surface of Jupiter. A lot more pressure, right? Okay. Example of what they might look like here for a cross flow. So if that was a typical lab dead end, here's a typical lab cross flow. In this case, and by the way, the place we put the membrane itself and how we arrange the plumbing can be different pretty often. So in this particular scenario, remember that we're going to have a membrane where it's not physically going to be this little diagonal typically, but we're just going to draw the schematic that way and say, all right, we've got a feed, a retentate, and we've got a permeate here. It's the last slide, don't worry. In this photo, we can see they've got a pump back here and a bottle of dirty water that they're going to treat, a permeate that looks nice and clean. And so essentially what we're getting here is a feed, a retentate. So that should be dirtier than what we started with in the permeate. Now the membrane itself is going to be in a nice little tube here. This entire system capsule is pressurized. The water's coming inside that tube. The pressure is pushing it through the tube, and the tube itself has a membrane at its surface. So clean water can make its way through that tube to the outside of that tube, and then it's collected. If you look closely, you can probably see it. It's like a clear plastic thing here, and you can kind of see, it's hard for me to draw a straight line when I'm looking that way. You can kind of see water is pooling right into here inside this clear plastic and making its way down. So kind of a neat little thing. There are different ways to set this up. We'll talk more about that next time. So we'll see you next Tuesday.